let's talk about the reaction of double bonds with bromine. We've already talked about the reaction of double bonds with hydrobromic acid, or HBr, right? So here, with HBr, we've got a clear positive end and a clear negative end of that dipole. My nucleophile, the alkene, is going to react at the positive end, the electrophile. Going to get this cationic intermediate. Again, these only last for a fraction of a second until something traps it. In this case, we are going to use the bromine minus that got kicked out as our nucleophile, Markovnikov addition of HBr. Okay? Now, what happens if I treat it with bromine? So bromine itself is a liquid. It's very, very heavy, and it looks like this. So is bromine polar? Well, yes and no. So it's not polar in the sense that there's a clear positive or negative end, right? But remember that bromine is polarizable. It's a big, fluffy electron cloud. So if I have electrons coming in, I can break this weak bond just like I broke that bond to give bromide up there. So the arrows are pretty much exactly the same between what I draw for HBr and bromine 2. But here is a pretty significant difference. Here, I added this hydrogen on this end, right? Again, there are already two hydrogens there. This hydrogen is too little to be on both this carbon and that carbon at the same time, right? And so we talk a lot about, okay, I have this free cation. And we talked about a lot of the rearrangements that cations can do and lots of the shenanigans that cations can get up to. Bromine is different. Bromine's a very large atom. And so we actually can have bromine kind of straddling both carbons at once. So here, I'm drawing a three-membered ring with bromine. Bromine's now got two bonds, so it's got a positive charge to it. It's going to break its octet rule, but remember, anything lower than the second row of the periodic table can break the octet rule, and that's fine. So I've got bromine with a positive charge. This is called a bromonium ion. And this is pretty stable. Again, a proton is too small to straddle both carbons at once, but a bromine is not. So they have this intermediate. Now, if you remember back to epoxides, we talked about, okay, when this is oxygen, I can have some nucleophile open the three-membered ring. All right? And again, I have a pretty good nucleophile, and so that is going to come and open this three-membered ring. So what happens when I do that? What happens is I get a dibromide. All right, so again, two bromine atoms added to what we call vicinal or neighboring carbons, like this. So again, HBr only adds a bromine to this internal carbon, but when I react with Br2, I'm going to get a dibromide here. Okay, so now let's make it a little more complicated and look at a cyclic alkene. So here's my alkene, here's Br2. Dichloromethane is a good solvent for this reaction. Usually solvents are not going to play a part in this. This is not a nucleophile, so we are not going to use it in any way. Here's my alkene nucleophile going to make a bond with bromine and get some bromonium ion. Now, this has a little bit of stereochemistry to it. Right? Three-membered ring. That bromine can form on the top or the bottom of the ring. So it'll be chiral, but racemic, plus minus. Okay? And again, very short-lived. Now, where is the nucleophile going to go? On this end or that end? Is this stereospecific? Really, what these questions are, is this an SN1 or is it an SN2 reaction? Here's our choices. We've got SN1, thinking about a carbocation. if I am actually going through a carbocation and not this weird bromonium ion thing, then I know a lot about this cation. I know that whatever adds next could add to either face of this thing, so it's not stereospecific. I'll get a mixture of diastereomers. I also know that the thing that adds second, again, in our case is Br minus, is going to add to the more substituted end of the alkene, which is to say here, right? The second bromine is going to go right there. Now, we can also think of this as an SN2-like reaction, but we get the opposite results, right? So SN2 is stereospecific, so we would only attack from the backside of this. We'd get only trans products, right? Because this is adding from the opposite side. But we'd only get reaction from the less substituted end, right? We'd say this is too crowded, and this is going to be where it reacts, all right? So it seems like this should be a pretty easy experiment, but it's not. So it turns out that when I react this with Br2, what I get is a dibromide where the bromines are trans to each other. All right, so this one looks like this is pure SN2, right? I don't get a mixture of stereoisomers. I do get a racemic mixture, which is to say my bromines can be like this or like that. But my bromines here are always going to be trans to one another. All right, so of these four predictions, it is stereospecific. It's not stereospecific. So, should I think of this as an SN2 reaction? Not so much. And it takes another kind of reaction to explain why that is. So here's a twist. If I run this in water, so if my solvent is at least a little bit nucleophilic, what'll happen is I'm going to end up with the nucleophile opening up this ring. So here, this is from the solvent. I end up with my OH trans to my bromine. This is called a bromohydrin, right? Because I essentially added Br and OH. Okay? What happened? So what happened is my solvent, of which there is a lot, is coming in and opening the ring stereospecifically, but at the more substituted end. So why is that happening? I thought that was too crowded to do any kind of backside attack-ish thing. Well, yes, but we have to remember that this three-membered ring is very, very strained, and this bromine is not going to carry all the positive charge. The bromine wants to share some of that positive charge with the carbons. And when it looks at the carbons it's bound to, and it says to itself, which of those carbons do I want to give this positive charge to? It's going to want to give the positive charge to the more substituted carbon, right? So this is already a little bit of a positive carbon. So that's what's driving the selectivity here. It's not that it's less crowded, it's that the positive charge here draws my lone pair electrons in. So we have this weird combination almost of SN1 and SN2 characteristics. Like an SN2 reaction, we're going to see stereospecificity. I'm not going to see a bunch of different diastereomers and scrambling. I'm only going to see bromine and my nucleophile trans, whether that nucleophile be Br minus or the solvent. However, my nucleophile is going to add to the more substituted end, not the less substituted end. And that's because of the buildup of positive charge on this more substituted end. Right? Sometimes we'll call this a loose SN2. Right? But the main point is bromonium ions open up stereoselectively, or stereospecifically rather. I'm only going to get trans products like this. but also whatever the best nucleophile in the pot, or the most abundant nucleophile in the pot, that's what's going to open it up, whether that be Br minus or whether that be a nucleophilic solvent like water or methanol or something like that. So very different from HBr, but the first step is the same. My alkene is a nucleophile. It's going to go out and grab an electrophile and break a weak bond.